very happy to have, sorry for my voice, to have Andrey Jivkov here, who will teach us about some discrete analysis of geometrical structures. What happens with geometry when manifold has gone? Okay?
Yes, thank you.
Thank you very much.
Thank you. You are one of the very few that pronounce my family name correctly. It's written with the French transcription because when I left the country, we had the French transcription of Cyrillic letters. So this is actually letter J, should be not J, not Jivkov. But anyhow, right. So let me start. I'm going to talk a little bit about combinatorial differential forms on cell complexes, where we started from, and then cochains and operation of quasi-cubical complex, which are going to represent combinatorial differential form on a more general complex. I'll talk about scalar transport on cell complexes because this is something that we've already done and it's dusted already. And then vector valued forms, vector and covector bundle valued forms, and something about obstructions like curvature and torsion. And I'll finish with questions that we are still working on and maybe somebody can help with some challenges with these forms. But the main question I started thinking about the need for a different sort of background representation, not background, but representation of physical systems is that we are not able to capture topological evolution. And almost everything that we see in material science is related to topological evolution. So when you have a standard differential geometry, you have a smooth manifold, you have a fixed background structure. Essentially, in engineering, this fixed manifold is Euclidean manifold. So it's tremendously easy to describe things. But the thing is that physical systems, in particular materials, age by changing the topology. And I think we have reached the limit to describe things in solid mechanics in particular, if we stick to this continuum framework. So then the question I ask is it possible to describe it somehow else? And the only thing I was thinking at that time was possible is to describe the material system as relational structures. And relational structures means things need to be described by the constituents of our material manifold. And those constituents are finite, discrete pieces. So I wanted to have something that is analogous to differential forms in the continuum case, and to operate with these differential forms. And I wanted to have analogs of connections, curvature, and so on and so forth. So our material now is a combinatorial finite cell complex, M, and this is our space. It's a relational structure. There is no background in space, embedding space. And this combinatorial structure, as many of you know, is composed of 0 cells, 1 cells, 2 cells, higher order cells. We work predominantly with 3 complexes, but this can be extended to any dimension. Or you can stay at a 2 complex, which is formed by 2 cells, 1 cell, and 0 cell, glued together by incidence relations. And the key point is that the physical quantities on my material complex M are represented as combinatorial differential forms, which were introduced by Foreman in, I think, 2003. And those, there is I'm not going to show a lot of formulas, just mostly concepts. So the combinatorial differential forms assign values to incident pairs of cells. For example, P cell sitting on the on the boundary of a P plus K cell. So to each such pair, there is a number assigned. So that's a form called combinatorial differential form. And of course, combinatorial zero form is assignment of scalars. Scalar combinatorial differential form, zero form, is assigning of scalars to each cell. That means to each 0, 1, 2, and 3 cell, and so on and so forth. And combinatorial one form is to each pair of P cell and P plus 1 cell, and so on and so forth. Two form is P and P plus 2 cell, and so on. These differential forms thus define the admitted exterior derivative, which was defined by the same person, Robin Foreman. And again, I don't show the formula, but you need to believe me, or I can give you the literature about that. It was very difficult to work with this form, already he admitted. So there is a suggestion that one can do a subdivision, which is topologically unique, by putting vertices in some sort of extended complex, which we call Foreman subdivision. I call it computational complex. Put vertices corresponding to each cell of M, and then put adjacency in the K reflects incidence in M. For example, if you have pairs of P and P plus 1 cell, there is going to be an edge or one cell in the extended complex. Whenever you have a pair of a P and P plus 2 cell, you're going to have a 2 cell in the extended complex, and there is unique correspondence. We're not talking about how geometrically that is later translated, but for the moment there is a unique Foreman subdivision. However, because we need to do certain operations, and in particular exterior product of forms, which you will see correspond to cup product of cochains in the extended complex, we wanted to have an extended complex that is quasi-cubical. This is the only restriction of what we do. Because exterior or cup product of cochains can be realized only for two things, for simplicial complex and for quasi-cubical complex. And because we want to have quasi-cubical complex, we restrict our M to be built of simple polytopes, which is not actually a big restriction, because most of the things in nature that I have looked at in materials look like Voronoi tessellation of space, and Voronoi tessellation of space produces simple polytopes. So for the moment, I'm not concerned about this to be a big restriction. But when we have this construction, combinatorial differential forms correspond to cochains, so the two spaces are isomorphic, and the exterior derivative of forms on M that are defined by Foreman correspond to co-boundary operators on cochains of K. This is, and as I say, the quasi-cubical structure enables a natural cup product. This is very interesting because it allows one additional thing that we didn't expect. It allows you to do transport on cells of different dimensions simultaneously in the original complex. If you think, for example, about a microstructure of a material, you have your grains, you have your grain boundaries, which are two cells in M, and so on and so forth. You have your triple lines where three grains and three boundaries meet, which is one cell in M. They become, so the transport through three cells, along two cells, and along one cells is, all these pairs are represented by one cells in K. So you can have transport formulated in K, which is a transport along cells of different dimensions in your physical complex. And I always think about what my physical complex represents. It must represent some physical system, right? In material, in my case. Not necessarily a polycrystal as the example, but some material. So then, this probably thing that you know, everyone. Should I explain chains and cochains? So chains is a formal linear combination of oriented P cells, just like that. and cochain is a linear functional over chain P chain is a linear combination of P cells, and cochain P is a linear functional on the space of cochains CP.
But your cells are originally not simplices, so they can be whatever.
They can be. They need to be quasi-cubical.
No, before that. So
Yes.
Before that, the original.
Yes. Yeah. The original the physical complex is a cell complex which is built of simple polytopes in order to arrive to K. Yeah. Yeah.
So the original cells are simple polytopes.
Yes. Yeah. And the K is a quasi-cubical, and so now I'm talking about K from this moment on.
But you're drawing simplices, that's why.
Well, this is okay. All the figures were produced by Azim, who sits there. And yeah, it's not a simplex. It's a quadrilateral in Oh, quasi-cubic. Well, quadrilaterals or hexahedrons. That's what I call by quasi-cubical. Anything that is.
But it's not cubical. No, not cubical in strong sense.
No, any hexahedron is a quasi-cube.
Hexahedron is six-sided.
Yeah, yeah. Any hexahedron, any quadrilateral in 2D is a quasi-cube.
But in high dimensions, what happens in high dimensions?
So what is in 4D then? A 4-cell that is quasi-cube. How many faces it would have?
Yeah, that's a must.
I can't say right now, but sorry. Yeah. It needs to be topologically equivalent to hypercube of dimension 4, right? So quasi-cube in one quasi-cube is just an edge, right? Yeah. 2 quasi-cube is a quadrilateral. Anything that
Just cube, topologically just cube. Combinatorial is just cube. No, cube I mean rectangle.
Oh yes, okay. So why should I call it quasi-cube? Okay, yeah. Probably I shouldn't. Okay, because I'm also thinking about the geometry after that. Fine. Yeah. Okay, so that's these are the chains and cochains, and then we do introduce a graded product, a cup product, and that corresponds to exterior or wedge product on forms on M. But what one caveat here is that this product does fulfill the Leibniz rule, but it's not associative, not in dimensions higher than 2. And sometimes I think I put this idea in correspondence or in analog with what is happening with octanions in Clifford algebra. When you go from quaternions to octanions, you lose the associativity, and I think this is what similar thing is happening here. So the product of octanions is not an associative operation. It is for quaternions, but it's not for octanions. So I think this is the difference here. So if you go in dimension more than 2, if you have a 3 complex and you want to do the wedge product twice, it's not associative. Luckily, we don't need to do it ever more than once, but I'm just mentioning this.
I just don't remember how to cubes, so I don't know. So, but for simplicial cochains, so the situation is that multiplication is associative but not commutative. So it becomes commutative only in the cohomology, when you pass the cohomology.
Yes, it's the same here. For the commutativity.
So maybe is it commutative? Well, in the
no, it's not. It's in the graded sense. It is, yes. It's graded.
But it's
graded commutative in the sense that you need to change the sign.
Yes.
Yeah.
But not associative.
It's not associative, no.
Okay.
So it's graded commutative. It fulfills the Leibniz identity, the Leibniz rule, sorry, not identity, but it's not associative, the product.
Yes. So it's different from what topologies I do.
It's different from the continuum, yes. It's different from the smooth. In the smooth case, the wedge product of forms is associative operation in any dimension.
Yes, but what I'm saying is that topologies, when they use cochains, they speak typically about simplicial cochains or simplicial single cochains. And in this case, the wedge product is associative. Not wedge product, but the cup product is associative, but commutative with a sign only up to algebraic homotopy. And here it looks like I never met cup product for cubical cochains. So I don't know from the top of my head. So, but it looks like you have this opposite sort of property. So it is commutative with sign, but not associative. Perhaps associative up to high homotopy, some homotopy.
I'm not sure about
Okay,
that.
well,
I can send you the definition of the cup product because we do use it for other constructions. Right, and so the next thing is, again, you know that boundary operators on chains, which form a chain complex, and the co-boundary that form a cochain complex. I will probably go quickly through that. And then we have the discrete Stokes theorem, which is the combinatorial analog of Stokes theorem written over here, one of the very few equations. And so in our case, this means that the conservation and compatibility are identities on our cochain complex. And this is why we use cochains. We don't build an analog of vector calculus, you build analog of exterior calculus in a discrete world. Okay. So I just wanted to mention here one point because a lot of people may have heard of discrete exterior calculus and the finite element exterior calculus. We do have some commonalities, but the major difference is ontological, in my opinion. Both discrete exterior calculus and finite element exterior calculus are discretizing a manifold, that there is already a background manifold, and doing a good job to some extent. But my thinking is that we need to be able to describe things intrinsically only through the elements of our structure. And so I keep insisting on that. I don't want to have a background manifold until the point I need to put boundary conditions. I want to have what is happening in the material knows only through the way it is organized. Okay, but we do have the cochain algebra is the same for us. The difference is that, particularly between discrete exterior calculus and us, is that in discrete exterior calculus there is a ad hoc correspondence between cochains in their complex, which is almost always, not almost, absolutely always simplicial, for the reasons that they need to build a dual, circumcentric dual. So it's a simplicial complex. They put correspondence between cochains of that complex and differential forms which live in some background manifold. They use some flat and sharp operators to move between the two spaces. And the other thing that DEC, for example, assumes is the DEC is not concerned at all about exterior product. They don't introduce exterior product of cochains, and they have an ad hoc definition of hot stars. Not through a metric or anything else, but just this is hot star, an area of of a dual element divided by the length of a primal element, or vice versa, or a volume of a dual element divided by the point weight, which is 1, and things like that. So there is an ad hoc definition of Hodge star. And it somehow, it's very nice. It leads to diagonal matrix for the Hodge stars, but we hit a block. We started with DEC many years ago in 2016, 2017. We hit a block, particularly when it comes to mechanics, but also for many transport problems. And we decided to move to this Forman idea of what is a combinatorial differential form. And then we had to introduce our own metric or inner products and so on and so forth, which I'm.
Because the Hodge star well, is related to underlying manifold structure. So if you don't assume manifold structure, you won't have Hodge star. So it's related to exactly what you said. So they have a restriction that they think that there's underlying manifold, and because of that, there is Hodge star. If you don't think, if you have just cell-cell complex, so there's no duality. So Hodge star corresponds to concurrent duality, which you don't have.
Well, we do have Hodge star. Yes, we define Hodge star. It's not on these slides, but yeah, exactly. It's similar. So I'll come to that. So what we think? So we started with scalar transport and scalar quantities on a cell complex, physical quantities. For example, certainly volume. It's a tree form. In our case, it's a tree cochain in K. But other things like energy, internal energy, it lives in the 3 cells of K, of course. So the top dimensional cells are hosts to extensive quantities. The 0-dimensional cells are hosts of their densities. And fluxes are something that lives on top dimension -1 cells. I always say, let's say 3, so the fluxes are attached to 2 cells, for example. And balance laws are expressed using just co-boundary operator. So it's very simple. Everything is algebraic. There is nothing special here. And what we do with the metric? So we introduce measures of cells, which may come, if you want to, by embedding your complex in a particular manifold, and say, now I'm going to take what I measure in that manifold to be the distance between 2 zero cells. I'll put it as a measure of the 1 cell and the area of my 2 cell. But it's not necessary. You can introduce any sort of measures to cells in order to be able to create curved things. And we have done that already, and it works perfectly. And then when we introduce these measures of cells, or weights, if you wish, we introduce inner product of cochains, P cochains. There is no formula here, but we introduce a scalar product. When we introduce scalar product, we introduce both a joint co-boundary operator, which is sort of corresponds to the co-differential on M, and Hodge stars, all of them, because we have inner product, so we can introduce Hodge stars. And there is so the correspondence here is between P cells and D minus P cells.
So you have some top degree, top dimension.
Top dimensional cells are, yeah. It's in our particular problems that this is 3. So you have a Hodge star D, you have a star 0 between 0 and 3. Yeah.
Yeah. Should we be imagining chains then as the analog of vectors?
Yes. Okay. That's according to Forman. Yeah. Chains are analog of vector fields. Yeah. Vectors, yes, not vector fields. That's right. And we have it in a moment when we want to introduce vector valued forms. So we have this machinery, and so we have the topology, we have the metric properties, measure, inner product, we have hot stars. And the last thing we need to formulate physical problems is a constitutive law between the fluxes, which are living on two cells, and the exterior derivative of the cos start from one. So this lives in one cell. This moves it to two cells, makes it a flux, and then there is a constitutive parameter. For example, if we're talking about heat transfer, this is going to be thermal conductivity of the material locally. So you can have it in every cell. It can be different, of course. So this is the constitutive relation, and we can form, again, no formulas, because if I put formulas, I will have to explain every symbol, and I don't have time for all these symbols. For what we have used it for quite a lot of things. So we have strong formulation, and we have the two weak formulations, integral formulations, primal and mixed. I don't know if you are familiar with this terminology. The integral, yes. But these are the strong for us. I mean, these are the truth for us. We prefer to do integration than to do the strong formulation. We prefer to integrate. So weak means that we use the integral formulations. Primal means that only the cos, the zero cochain is unknown, and the fluxes you need to solve. You need to solve for the zero cochain, and fluxes come out of the solution. Mixed formulation means that you have both unknown, your cos and your flux. For example, temperature and heat flux, or concentration and diffusive flux, or whatever the scalar problem is. And these are typical things in finite element methods. They're both used. And the absolutely best is the weak formulation, the mixed weak, because you have ability to fix both boundary conditions. Exactly. Because you can impose boundary conditions on your primal variable, and you can impose boundary conditions on your flux variable, the derivative of the primal.
Excuse my ignorance. So, but when I have differential equations, it's very easy to realize the difference between a strong and weak, because either have solutions which are actual solutions as well, smooth functions, or you rewrite your differential equation in integral form, and basically you're looking for solutions which belong to some space of distributions. But here things seem to be finite dimensional if you have space of cochains, right? Is it finite dimensional?
Yes, it is finite.
But then what's the difference between elements of the space and distributions? Because both finite dimensional spaces should be the same.
Right. So the terminology, this terminology is borrowed from finite elements, where the space is also finite dimensional. It's finite number of elements. It just means that instead of writing putting it in a differential form, which I can demonstrate that. For example, maybe here. So if you have a scalar primal variable which is going to sit at 0 cells, and you take the exterior derivative with the co-boundary of that, you're going to put something on the 2 cells. The strong formulation will be, I'm going to use that and just do the divergence, exactly as one would write divergence of the gradient, right? And I'm going to put some properties on the 1 cells just to multiply the exterior derivative by this property. And when I diverge it, I'm going to get to the 0 cells, because I'm going to use d star, the codifferential. That's the strong formulation. The weak formulations are integrating into the 3 cells, which is the true physics, by the way. You're conserving the quantity, for example, heat energy, thermal energy in the 3 cells. The strong formulation corresponds to continuity, I would say, while the weak formulation corresponds to conservation. You see, the weak formulations are using the delta 2 of the fluxes to conserve whatever the quantity is, heat or mass, into the 3 cells, in the sense that whatever comes in should come out, or there will be a change inside, right? This strong formulation is not a conservation law. It's a continuity in a way, because you're going from 0 cells to 1 cells, and then you're diverging to 0 cells. It's diverging in the sense that you're moving with the co-differential. And it's less physical, not so close to the intuition what the conservation should be. That's why I say we like more than. And also, this gives better results computationally, which we have shown in the paper. Okay, so this is the difference, the way we think about what is strong and what is weak. Strong is just mimicking really the differential equation, which is du dt is equal to a nabla dot of parameter times gradient. That's what the strong formulation is mimicking. The weak formulations are mimicking the integral versions with test functions, of course, exactly the same way as it is done in finite elements. Sorry? They are not, but these are better. This is what I'm saying. And they're closer to the physical, the way you think about conservation. So we have applied it to quite a lot of problems, diffusion in heterogeneous complexes, both mass diffusion, heat conduction, charge transport, several works on flow in porous and fractured media, a couple thermochemical transport, and I mentioned this here and here again. The mixed forms are better computationally. As I say, you can particularly the mixed weak, you can enforce both Dirichlet and Neumann exactly. You can't do that with this one. With this one, you can enforce only the primal variable, so the Dirichlet. So the mixed weak is the one that I would recommend. Are you okay with this? No.
Well, we have to. I don't know the final element method, so therefore I don't have the background to just properly appreciate that. So, but I don't want you.
These are. Yeah, but all right. So those are also called variational formulations, right?
Yeah, but well, the reason why I was asking, so which probably don't something that I don't understand. So maybe there's some difference in computation viewpoint. But what I was saying that when we have actual differential equations, where this comes from, so that's the difference can be because you consider this for different classes of functions. So the strong solutions in the world of linear partial differential equation means the solution is smooth function which satisfies or field that satisfies the equation. And weak means that you, after your equation being written in integral form, so it's actual the solution is initially belongs to some sort of space of God knows what, so distribution of it, and they're not the same. They maybe some weak solution may turn out to be strong because of some some ellipticity condition of, again, God knows what. So some functional analysis result. But the main difference is because you're working in infinite dimensional spaces where there is a big difference between the space, say it's dual. Here, at least apparently, so perhaps I don't know some important element, right? So apparently here it looks like, because we're talking about fine dimensional case, there shouldn't be any difference between, well, test functions or some and it's dual space or something. But perhaps there's some bulk of some piece of information which is missing from my feature. That's why I'm asking. So, but I cannot. Well.
Right.
I just want you to
I get- I- I-
to lecture me on some days.
I guess, yeah,
let it go, move forward.
I guess there is then a problem with terminology. That's why I tried to explain. So what we mean by strong is a direct mimicking of the differential equation, right? Which is not a conservation law, by the way. Differential equations are not, they are continuity equations.
Equation can be whatever, so it's
In these cases of transport of scalar quantities, they just say that what comes into this point needs to go out. This is the meaning of when you write it in a differential form. But you cannot write a conservation for a point. There is nothing in a point. The physical thing is that you need a volume, and you need something to get in and something to get out. And in that sense, so there is a terminology, you're thinking about something else and I'm thinking about something else, right? So the weak formulations, we call them because the finite elements call them that, are the ones that conserve the quantity in 3 cells, and the strong formulation is a simplified form, which is not exactly a conservation law, it's a continuity at points. This is the way I could explain it. Right, so, but we had to move to a point, what do we do with mechanics? And it's tremendously more difficult. So we had to introduce some vector and covector quantities for the reasons that we are aware from exterior calculus attempts to formulate, for example, elasticity, not attempts, it's been formulated, that we have displacements as vectors. If displacements are considered as vectors, then the forces need to be covectors, linear functionals, and then we know that displacement gradients are vector valued 1 forms, and we also know that what is stressing the continuum is a covector valued 2 form. It's a linear operator on infinitesimal areas that produces a force.
Yes, stress-free tensor.
Yeah, it's a linear, but it's a linear operator that takes an infinitesimal area and produces a force. And in our case, this is a covector valued 2 form. And so, we don't have an ambient tangent bundle, and we need to use only the things that are in our structure. So we introduce vectors to live in the fibers attached to vertices, practically. Okay? We need to introduce vectors in some way, and there was a good question whether chains are vectors. Yes, but in our case, we use it in this way. We attach a vector space to each vertex. So which means all the vector space is all linear combinations of the adjacent 1 cells. Okay, that's the fiber. That's a fiber at vertex V. Fiber at vertex V is all linear combinations of the 1 cells attached to that 0 cell. Okay? They become of different dimensions. This is the difficulty, right? So the dimensions vary. So there is no canonical identification between fibers. But you build this fiber bundle, and the section of the fiber bundle is your vector field. Any section, a section of the fiber bundle is a vector field, because that gives you a particular linear combination of 1 cells at each vertex, which is a chain, local chain, right? So local 1 chains attached to each vertex, that's our fiber bundle, and then we have the section of that fiber bundle is 1 vector field. So this is the example that they can be of different dimensions. You can call it a tangent space, right? You can call FV a tangent space at vertex V, and then the dimensions of these tangent spaces may be different. They may not be different only if you have a regular grid, a cubical or a square grid in 2D, then you don't have a problem with the fiber dimensions. But we don't want to have that only. So yes, I just said that vector field is a choice of element, and we need a connection. And we need a connection because we need to be able to build covariant derivative of a vector field, which will represent our unknown displacement field, for example. You can think of it, I have this point, and what is the displacement in this point? The material will think, okay, I can move that much along this edge, that much along this edge, that much along this edge, and these numbers are the coefficients of my linear combination. But how do we differentiate this? We need the transport map from one fiber to another, and in order to be able to find what is, essentially we need to be able to compare the one fiber with another, right? In order to make the difference. And we have several approaches which I don't show here, but I can explain them. And of course, the simplest approach is to say, okay, I'm going to compare only the coefficients of the two fibers that belong to the edge that is. If I want to move from this fiber to this fiber along this edge, I'm going to compare on the coefficients that multiply this edge only. That is not going to solve the mechanics problem at all, because you're going to represent only the axial deformation, nothing else. So you need something more. And what is more, but still stay a little bit close to the structure, is to say, except or in addition to comparing these coefficients, I'm going also to say that any one cells that together with this one belong to a two cell, I'm going to compare them. So I will be able to make a transport. Okay, and then in addition to that, we could introduce metricate fibers. Maybe I have a slide for that, so I'll come to that. But before that, right, so I spoke about that. Connection is assignment of linear maps. And then if we have these transport maps, again, this is given for 3 fibers, but it should be for 4. Should be for 4. And you go around your quadrilateral with your transport maps, and you apply them one after the other. You make a composition. You're going to come up with, well, it doesn't say, it shouldn't be here identity. It's not, yes. Okay. Something else. So you come up with the composition of the transport maps. It's very similar to what you do when you consider curvature in the continuum, but then you squeeze that area, that 2 cell to 0. You know, you consider infinitesimal area.
Because they're not necessarily the same dimension, not necessarily isomorphism. So if you go one way and it's not the same as going the other way, which will be inverse. So because they cannot be inverse in general.
This and these are not inverse. Yeah, but if you go this way and you go this way, you're going to get an endomorphism. You're going to get a map that is equal to dim FV times dim FV.
Yes. I mean, this what is lost in comparison with ordinary connections is the fact that there are isomorphisms between fibers, because you cannot assume that.
Yeah. But you're going to, so you when you start from this fiber, you're going to get one endo. I see what your point is. Whether you start from here or from another one, you're going to get, and this is the thing, you're going to get one endomorphism for each of the vertices of your quadrilateral. If you start from this vertex, you're going to get one endomorphism. If you start from this, you're going to get something else. Your Riemannian curvature, or discrete version of Riemannian curvature, is the 2 cell plus 4 endomorphisms. That in the continuum, because you shrink the area to 0, it become 1. You have, so I should have probably explained that. I spoke about what is a vector valued 0 form, which is a vector field, right? A section of vector valued 1 form is an attachment to each pair of 1 and 0 cell, a linear combination. So a vector valued 1 form means if I have this 1 cell, to this 0 cell I attach a linear combination, I attach a vector, and to this I attach a vector. So this 0 cell is not going to have 1 vector attached, it's going to have as many as 1 cells are there. Each pair of 0 and 1 cell.
Wait a minute. So cochain, so 1 form is a cochain, right? Cochain. So that means a linear function on your edges.
This is the scalar, yes. This is the scalar 1 form.
Yes,
we are now talking about vector valued 1 form.
A vector valued 1 form.
Yes.
Right?
So the vector valued 1 form means that to each pair of 1 and 0 cell, I attach a fiber or section of it.
You have an edge, so you have 2 endpoints.
Yeah.
Points.
Yeah.
The,
Yeah.
The source and target.
Yeah.
Right. And so what do you attach to that?
One linear combination is related to the pair of this 0 cell and this 1 cell, and another linear combination to the pair of this 1 cell and this 0 cell.
Okay, so basically 2 vectors and
yes, yes, at the 2 ends. The same is for 2 cells and the 3 cells. So a vector valued 2 form will be to each pair of 2 cell and a 0 cell on its boundary, I attach a vector here. To the next one, attach a vector here and a vector here and a vector here. But the same goes for endomorphisms. It doesn't matter what I attach. So when I say an endomorphism valued 2 form, I mean that to each pair of 2 cell and a 0 cell, there is an endomorphism attached. And this is what happens if you do this process of composition of transport maps. Starting from here, you're going to get 1 endomorphism, one algebraically a matrix here. Starting from this fiber, you're going to get another one, and so on and so forth. And you're going to get a endomorphism valued 2 form, defined previously as what is an endomorphism valued 2 form. Okay, so an endomorphism valued 0 form will be attachment of a matrix to each 0 cell. Endomorphism valued 1 form will be attachment of a matrix to each pair of 1 and 0 cells. 2 form and so on, and so in 3 form if you want. Okay, I say form all the time. I mean cochain. Okay, in K. Sorry.
Has to be
Incident pairs. Incident pairs. Yes. Yeah. Yeah. So. Yeah, so this is wrong. It's not identity here. It's a composition of transport maps, and the curvature is defined by the deviation of this composition from the identity. So that identity there was wrong, right? Curvature is that composition minus the identity at that point. So essentially, you can have a situation where the curvature has a 0 value at one of the nodes of a 2 cell, but not 0 values at another, and the third and the fourth. I don't know how this goes into limit of the continuum, how these 4 different endomorphisms move into one when you shrink the area, but we don't shrink the areas. The areas are finite. We are talking about finite complex. Okay, and we also have a construction for torsion, which we interpreted as compatibility defect. Why I bother about torsion and curvature? People will ask. Because the materials have them intrinsically. I don't know if you know this, but the material space is not even Riemannian, it's not even Riemann-Cartan, it's Riemann-Cartan veil. It has non-metricity because of point defects, it has torsion because of dislocations or uniformly distributed dislocations, it has curvature because of gradients of dislocations and other things, disclinations, for example. So the material space itself is not, it's a very complicated, even if you think of it as a continuum, it's a complicated structure. And when we want to represent it as a assembly of discrete entities, we need to have these things defined in order to compare with, in the future, with what we see, what we can measure. We can measure dislocation densities, we can infer from EBSD maps. And we want to be able to relate experimental evidence or pictures with the way we model. Yes. Well, here we have, to introduce the torsion, we have a very simple idea of solder form in order to produce torsion. And the solder form is just to each pair. Solder form is a vector valued one form, right? Solder form means that to each pair of one cell and zero cell, the linear combination that you attach is just this one cell. One times that one cell. That's the solder form. And through that solder form, we can define torsion. We also have introduced a bracket, antisymmetric bracket, but on the vector fields, on vector fields, yes. Vector fields now we can, so that means vector valued zero forms, right? Zero cochains. But it does not fulfill the Jacobi identity. It fulfills something that is a little bit extended. Again, for all things, I can send you the exact formulas later. I don't know whether this is very important or not, because I don't, at the moment, I don't see where we need to, we would need it if we want to do exterior product of vector valued forms, right? Because if we want exterior product of vector valued forms, we will need to multiply the vector legs, so to say, through this. The form legs we have, we know how to multiply the form legs. We have an exterior product of forms. But the vector legs, we need the bracket. I have not thought that far, but we do have a bracket if you want to look at it as well. I need to finish probably soon. And then the other thing I already mentioned, that if we want to we can transform, we can create transport maps which are metric compatible by introducing metric on the fibers. So we just say, this is the way I multiply two vectors belonging to this fiber. So for each zero cell, I can have a metric map, a symmetric bilinear operator, or whatever you call it. So we can introduce this and make the connection, or the transport map compatible, and from there the connection. But it's not clear whether we can keep the. So essentially, what is going to be the difference if I introduce the metric and I don't introduce a metric in the way I determine curvature? The curvature should not depend on the metric. So if I introduce a metric here, will I get the same curvature? I don't know. The Riemannian curvature should not depend on the metric at the end of the day, right? maybe on the way, but not at the end of the day. And here the question is, I can calculate the curvature through the procedure that I just showed with multiplying a composition of transport maps. I can modify the transport maps to include the metric so that I can compare two fibers having in mind their metric locally defined metric. But if I use the metric modified transport maps, do I get the same curvature matrix?
Are you saying that you are introducing a connection compared with metric?
Yeah, yeah. Transport map, and from there the connection, yes. Transport map, or way to compare two fibers.
But curvature depends on connection, so whatever connection you choose, it will give you a different curvature. So if you just choose a connection somehow compared with metric, then
oh yes, you are right. So it's going to be different.
Yes, it should be different. So, but if it is compared with metric, then it should be monomorphism at least. So this because otherwise, well, it won't be isomorphism between different spaces, but in one direction it will be without kernel, and nothing's mapped to zero except for zero.
Right. We need to think about these things. Yeah. Okay. So there are things here about again, these two cells should be four things. There are things that we need to think about, and in general, I already spoke about this actually. Why mechanics cares about curvature and torsion. So I'll skip that slide. So what we don't yet know fully is what are the admissible wedge transport maps. So I mentioned two. Are they sufficient? There are other things that are related to the metric. At the moment, our metric is what do we call it? Orthogonal? No, diagonal. But it's not enough, I think, and it's not enough even for the scalar case. When I say diagonal, I mean that delta ij, sorry, a basis vector times another, ei times ej is delta ij. That's what I mean. So one cell times itself is one cell times another one or the length squared of that cell.
Yeah, you mentioned before measures that you attach to
yes.
So diagonal rather than just.
But that is one possibility, to say that my metric tensor is this one, right? Formed by ei times ej. Scalar product of ei times ej is delta ij, but it may not be sufficient for mechanics, and one might need to include angles, which are sort of measures of the pairs of 0 and 2 cells, rather than saying angle. So you have measures on one cells, you have measures on 2 cells, which are areas. You have measures of 3 cells, but maybe you need to introduce measures between measures of the pairs of 0 and 2 cell, which is sort of measuring the angle, into the scalar product, and say now if 2 1 cells belong to a common 2 cell, then they have a scalar product, and that scalar product is dependent on that measure, something like that. Yeah. Now, this is really not a question now, because we know, well, not fully, but if there is a better way to define solder form, maybe there is a better way to formulate torsion. And at the end of the day, what we are after is what is happening to all the structures when this complex is evolving, because we want to be able to represent fracture. Any rearrangement, actually, splitting, refinement, whatnot. Okay, so that's it. Thank you very much.
Yeah. When you define vector fields,
yeah,
I can't help but notice I'm not sure if perhaps you can convince me. I'm not sure I agree with how you define a vector field, because it seems to me like, so you called them vector valued zero forms, which is, at least in sort of geometric manifolds, that's a very different thing to a vector field.
No, it's just the same.
It is the same.
It's exactly the same. To the point you attach a vector.
Yeah, it is the same. They are isomorphic things.
But surely a vector valued zero form would be a section of, say, a trivial bundle.
No. No. The vector values, it means taking values in tangent bundle.
Oh,
so it's a tensor with just one upper index.
All right.
It's the same thing.
Yeah, no.
Similarly, the other thing that we were thinking about exploring is when we were talking about displacement gradient. The displacement gradient is from one side a vector valued one form, but it can be actually represented uniquely as a endomorphism valued zero form.
Okay.
And it is similar to the continuum, because in the continuum, this is a strained tensor, or displacement gradient is a tensorial quantity, right? And that the meaning of that tensorial quantity is that it eats a vector and returns a vector. Essentially, it eats a direction and then says how much the vector changes in that direction. A vector would change in that direction. How much is the displacement changes in that direction from here to here? So there is a displacement change, and that displacement change is the vector, the split out, the output vector, right? So it eats a direction, it gives you a displacement difference, so to say. But when you teach the students, you say this is a tensorial quantity is defined at a point, and there is a unique correspondence between a endomorphism valued zero form and a vector valued one form.
Yes.
Yeah.
What do you know about existence of connection or connections that are compatible with the metric, right? Yeah, that's what I'm saying.
What do I know?
Yeah,
Do they exist? Do they exist necessarily?
Probably not.
So we can make our connection compatible with the metric by construction. We can construct the transport maps. They are going to be different for each pair, for each cell. One cell, there will be a transport map that is that can be made metric compatible. But when you say Levi-Civita, if Levi-Civita is also torsion free, I'm not sure that our metric compatible connection is going to be torsion free. That's a different story. So yes, if we don't make it metric compatible, if we use combinatorial connection as I defined it, there will be some curvature, there will be some torsion, possibly, I don't know. But if you make the connection metric compatible and you follow the same procedure, maybe the curvature is going to be different, but maybe the torsion is not going to vanish. In a way, we want to eventually link, we want to somehow learn from maps of microstructures what is the way we should differentiate. It's an inverse problem eventually. So I have a reading and I can say, well, there is a dislocation, geometrically necessary dislocations are called density. I measure here and I measure a gradient. Can I construct my connection? Because the connection eventually determines how I'm going to do the mechanics. This cannot be done in continuum. You cannot move anything back. You don't know. I don't know how to explain this. This is a tricky situation. In the continuum, all the continuum mechanics works with some smooth space, with predefined structure, predefined metric, predefined way you differentiate. And how do you put some information from outside that says, well, that's not the way you do covariant differentiation. The way you do covariant differentiation is dictated by the material, not by you, not because you assumed Euclidean space or some Riemannian space or something. Is dictated by the material, and it may change from one grain to another to another. So that's the idea, is to be able to describe better the material and the behavior by taking into account what the material tells you, that the way you need to differentiate or integrate, for that matter, and to do analysis. I think this is the final point, but we are, I think, far from that.
But which properties of material do you ascribe to the cells? Because cells is just combinatorial structure.
Okay.
But if you want to describe some material, so you need to attach something.
Yes. Yeah.
So, what exactly do you ascribe?
So as properties, for example, in the case of let's say heat transfer, your three cells are going to have assigned heat capacity, for example, density of the material that they live there. So are we talking about K or M? In M, every cell, for example, every three cell may have a thermal conductivity, but also every two cell, it can have its own thermal conductivity, because you may have a different way of heat transfer on a two cell, because a two cell represents something physical. It's a different phase from the bulk.
So your actual piece of material is represented by what you said in the very beginning. So your M, right, from which you produce K.
For computational reasons, yes.
Yeah.
We just don't.
You may think of this M as actual pieces of the cells of M as actual pieces of material, like grains or whatever.
Yes.
Just adjacent to
yes.
each other with some physical properties.
Yeah. And again, typically, the cells of different dimensions represent different phases, and this is true in the materials. So a two cell may represent a grain boundary, and if it represents a grain boundary, that grain boundary is its properties are different from the bulk. Both thermal, mechanical, all properties are different, but they are also different from one grain boundary to another, because of the way the crystallographic orientations of the two grains determine what are the properties of the grain boundary. It may be more cavitated, it may be less. So you can think of its different phase. There may be difference between the two different grains, because in this grain you have higher density of dislocations, lower. So each grain may be different from each three cell in M may be different from another. Each two cell in M may be different from another two cell and from the three cells. And each one cell, triple line, some people call it triple junction because they look only in 2D and it's a point there, but in 3D it's where three grain boundaries meet and three grains. It has its own structure. It's a different phase, and each triple line can have different properties from the other triple lines, and certainly from the grain boundaries, from the two cells, and certainly from the three cells. So you can put properties to each individual cell, physical and mechanical properties, and then those are transported to K for computational purposes. Yeah. So that's the point, is to make something that we can reach a little bit deeper into the way we describe materials than what the continuum allows us.
I wonder how all the, say, failures of Jacobi identity or similar things, what happened with them? Apparently they're supposed to shrink to zero. But on the way, there must be something which, you're still, like first order approximation, you shrink them to zero, right? So something which is responsible for this failure of Jacobi identity. something which does not exist in the continuum situation, but which is responsible for this failure of Jacobi, like some operation with 3 inputs or something.
Yeah, I don't have an. So there is just one additional term in our definition that is absolutely necessary in our definition of anti-commutator that spoils the thing. We originally I invented something that fulfilled the Jacobi identity, but one of my collaborators said, "Oh, but that's not that anti-commutator doesn't capture all the things, so to say. There should be additional term, but with this additional term, is you don't fulfill the Jacobi identity." Now, I don't know whether in the limit, I personally don't know how to do a limit here. I am thinking the other way. I'm thinking that actually the continuum is the limit to this, but in the other direction. You need to have infinitely many cells to be a continuum and not squeeze this to be to zero.
That's right. You have some finite volume, but you multiply the number of elements within this volume.
Yeah.
Wouldn't it be easier to take if you like if you avoid all the dimensional issues, but just using a grid? Because to me, like if you're trying to take the limit, right, the big issue we run into is two zero cells coming together that have different numbers of edges. You can't coincide their tangent spaces. If you start with a grid, then maybe it might be easier to do that.
Yeah, maybe.
Uniform grid.
I don't know. I just think that playing with sizes rather than numbers is not going to work. I mean, just saying I'm going to shrink my 2 cell now to 0, because that's the key point. We are building the things around the 2 cells. You need to have a loop. Just saying I'm shrinking it to 0 is, what are you going to find there? I personally think that you need to say, if I now make, it's combinatorial. I cannot shrink it because it's combinatorial. So I need to have many. And if I have many, is something changing for the situation. If I have too many, maybe this is becoming closer to one value. I don't know how to think of actually about that. Subdivision. Yeah, but subdivision means. Yeah. I see. Okay. Yeah, maybe. Still keeping it finite, right?
Yeah.
Sorry, yeah.
This might sound like a slightly unhinged suggestion, but basically you're trying to deduce bulk properties of a material from the grains, right, of the material, or like from the interaction between grains.
Yes, initially.
Yeah. Well, this sort of sounds a little bit like there are some theoretical physicists that are basically trying to do the same thing, but with space-time.
I know very well. Yes.
Right.
Yeah.
And so this maybe just think now of spin phones, which is I think what they're called, which are basically I think the sort of idea that you have like this very granular nature of reality, but at very small scales.
Yeah.
And that once you build it up, all of the properties of space-time emerge from this. And it sounds sort of like the same thing.
Conceptually, yes, I have seen that. I have seen a particular loop quantum gravity, but this is a little bit more practical. I know, but they want to derive the geometry out of these structures. They want to have metric coming out. I'm not that ambitious. I want to be able to put the measures of cells, because I'm trying to model something physical. But I understand that there is an analog to.
But in terms of this argument about turning into a grid or shrinking things or blowing things up, I think it's sort of an interesting analog, right? Because
Yeah, maybe we should think in that direction. subdividing, see whether something changes.
Divide M perhaps rather than K. Because
No. K is better to subdivide because it's already cubical. So it's going to continue to be cubical all the time. I think so, yeah. So, yes. Well, I want to learn things that we don't know. The things that we don't know is where and why the materials fail. There is no convincing theory. I mean, we have fracture mechanics, that's my area, but in fracture mechanics, you need to have a crack, you put it in advance. But why does it come into existence from nowhere? There is no theory that, so there are no explanatory theories at all. So everything in most of engineering is curve fitting. Okay, you invent, because what the continuum offers you is a stress tensor. The stress tensor is symmetric. It has 3 invariants. The only thing, the so-called constitutive modeling in solid mechanics is what function of the three invariants of the stress tensor we can devise, invent, and let's suggest this function. And then we start, we do finite element analysis, and then we start curve fitting parameters of this function to experimental data. There is no explanation here, right? And then you say, oh, it doesn't work, or it works. You fit it for uniaxial case, uniaxial tension. You want to apply to multi-axial, it doesn't work. Why? Because this is not the function. And then you say, okay, I'll introduce another function. Again, a function of the 3 invariants. That's what you could do. This is the only thing, because it's a continuum, because it's homogeneous, you have the same thing at each point, and the points are infinitesimal, and each point has infinitesimally many neighbors, and the next one, this is the only thing you can say. But it's not going to explain why I got failure starting here but not there. And fundamentally, you can. So you need to say, okay, I do need to have some structure here, which is going to guide me. And the structure is, I'm not saying the cell complex is the only possibility, but you need to have some structure, underlying structure, that is going to guide the evolution of that material or our cells, for that matter. I know you did work on cells, biological cells. So you need to represent it as a structure, and then I say, okay, but I need to have this structure to be or my analysis to be as little dependent on assumption of a background as possible, if possible at all. Shouldn't be. That comes from some sort of fundamental requirement in physics to be background independent, as far as I believe. And this is where it started. We cannot describe anything in a way that explains. We are just looking into some constitutive relations, and then curve fit parameters, and people start increasing the parameters because they cannot. When you see something with 12 parameters, is that really a law? Is that really a constitutive relation? Something is not right if you have to fit 12 parameters, or 6 even, or so. I think, I don't know about fluid mechanics, but I think we have a lot bigger problem in solid mechanics than fluids.
More questions, please?
Yeah.
If there are no more questions, let's thank the speaker.
I'm sorry I took a lot more time than necessary. I think we were supposed to finish by 4.